Hi guys, welcome to the 7th renal lesson and the last one, blah, blah, blah. This lesson will cover renal handling of acid and base. The kidneys are a fairly important component of how the body handles acid-base problems. And although this lesson is not meant to be a comprehensive coverage of acid and base, we'll introduce a few concepts and talk about the kidney's role in that without going into too much depth, which we'll save for the acid-base section of the curriculum, which is coming up. Okay, so first of all, some background. In the notes, I have 7 points that sort of like are general points about how the body handles acid and base. The first 3 I hope are definitely reviewed. Things like pH is the negative log of proton concentration. If not, please read that over. The last four are perhaps a little bit less basic, and something that we kind of want to talk about up front before we start talking about the other aspects of renal handling and problem. First of all, the most important pH buffer system is the carbon dioxide bicarbonate system, and arguably this is the most important chemical equation in the body. This is the conversion of carbon dioxide and water to bicarbonate. It is catalyzed by carbonic anhydrase, and this is how the body buffers protons. In other words, bicarbonate is the major proton buffer in the plasma, and it regulates what the free proton concentration is going to be, and we'll talk about that in a moment. Carbon dioxide is a gas, so it's regulated by the respiratory system. We aren't going to talk a lot about that. But we are going to talk a lot about how the body handles bicarbonate, and the kidneys have a major role in doing that. So a couple things to note here. If you add a fixed acid to the body, that is a proton bound to an anion like chloride with hydrochloric acid, or like lactic acid bound which is protons bound to lactate, that would be an example. Those are examples of fixed acids. If you add a fixed acid to the body, the bicarbonate level drops always, okay? This equation tells you that. If I add hydrogen ions, protons, I shift this equation to the right, and I produce more carbon dioxide, and that's because protons bind with bicarbonate to do that, so this bicarbonate disappears when I add protons to the system. Bicarbonate levels go down when you're adding acid. If you decrease fixed acid, that leads to decreasing protons. That shifts this equation to your left, or your right, as you face the board, that way. It shifts the equation that way, and you produce more bicarbonate. So your bicarbonate level goes up when your fixed acid goes down. That always happens, okay? This is the physiological buffer, and this is how it works, okay? So when we talk about keeping proton balance in the body, which is what we're measuring with pH, what you're also essentially talking about is keeping bicarbonate balance, and the kidneys are a big part of that. And finally, note this last point where the Henderson-Hasselbalch equation lies. This is the equation used to calculate pH. You must memorize it, okay? And it is 6.1 times the log of bicarbonate, the normal level of bicarbonate, 24 millimolar, divided by 0.03 times the partial pressure of carbon dioxide, which is about 40 millimolar. And when you look at just that part of the equation, just that ratio, normally it's about 20, okay? And if that ratio is 20, then you've got a pH of 7.4. If the bicarbonate is high, this ratio is greater than 20, and your pH will be greater than 7.4, and you will have an alkalosis on your hands. If the bicarbonate is low, this ratio will be less than 20, the pH will be less than 7.4 in the plasma, and you'll have an acidosis on your hands, okay? So this ratio is the key to the equation, all right? All right. You will note that you gain acid in your body by a variety of different ways. You take acid in, particularly if you eat meat, about 20 milliequivalents per day. Your metabolism produces about 20 milliequivalents per day of hydrogen ions. You lose bicarb in your stool, which is equivalent to gaining acid when bicarb goes down, and protons go up. And so that is equivalent to gaining 20 milliequivalents per day of acid. So you add all these up, there's 60 milliequivalents per day. In order to maintain an acid balance, you have to get rid of 60 milliequivalents per day. The kidneys are the way that you do that, which is why we're talking about this, all right? So let's talk first about how the kidneys handle bicarbonate. And then in the next video, we'll talk about how your kidneys excrete acid, which is equivalent to also handling bicarbonate, as I just said. And then in the last video, we'll sort of put it all together and look at the kidneys and the big picture of acid-base control without getting into too much detail. So here's our bicarbonate handling. The first thing you will notice is that if bicarbonate is normal and you're at a normal pH, the bicarbonate is almost all reabsorbed, all right? 80% here, 15.5, almost all of it goes, all right? So it's freely filtered. The concentration in Bowen's capsule is the same as the concentration in the plasma. It's about 24. Pretty much all that 24 is going to be reabsorbed in the kidney, okay? Bicarb is generally conserved, particularly at normal pH, all right? Generally. So most of the bicarb is reabsorbed in the proximal tubule, about 80%, right? So, you will note in a minute that always involves a proton secretion step. So we are secreting protons, moving them from the plasma into the, or at least from the cells, into the renal tubule. At the same time, we are reabsorbing bicarb. Let's take a look at how this happens. The reabsorption in the proximal tubule is transcellular, okay? And as is usual, it is powered by the sodium-potassium ATPase, the basolateral membrane. It maintains it, that generates a sodium gradient and maintains it. Low sodium on the inside, high sodium in the interstitial space. That drives secretion of a proton, a hydrogen ion, okay? And that's because sodium flows down its concentration gradient, and that allows you to move hydrogen ions from high concentration in the cell to low concentration in the tubular lumen. In the cell, pH about 7.2. In the tubular lumen, particularly after you've just filtered plasma, it's the same as the plasma, 7.4, okay? So there's your hydrogen ion secretion step, okay? After you secrete hydrogen ions, here's where your carbonic anhydrase equation comes in, where you take filtered bicarb that combines with the hydrogen ion that you just excreted, and you generate water and CO2 right here. Water and CO2 are permeate to the apical membrane. You don't need a transporter. They diffuse across the membrane, and they reassociate in the cell to protons and bicarb. The reverse of this reaction takes place inside the cell, okay? And then you will note that your bicarb is transported into the interstitial space. So in effect, we've taken a filtered bicarb and we have transported a bicarb into the interstitial space by bicarb reabsorption. But note that this bicarb is not the same as this bicarb. This bicarb became carbon dioxide and water. This bicarb came from reabsorption of carbon dioxide and water inside the cell. So there's no, quote, bicarb transport step across the apical membrane. The transport takes place in the form of diffusion of carbon dioxide and water, and then your bicarb is reabsorbed across the basolateral membrane from there, all right? Notice what happens with your proton here. It is reformed in the cell, and then the same proton could be transported back out through this sodium hydrogen antiporter into the tubular lumen. So this is a form of hydrogen ion recycling where the same hydrogen ion can go here, 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 here. And you just recycle it over and over again to transport bicarb, a net bicarb, across the epithelial layer. Sometimes this is referred to as the proton crank or the hydrogen ion crank because it's a recycling of this ion, okay? All right. So that was the proximal tubule. Let's take a look at reabsorption in the collecting duct. This is done by type A intercalated cells, okay? And first of all, you will notice the absence of a sodium-potassium ATPase in the basolateral membrane of this cell type, one of the few in the body that does not have a sodium-potassium ATPase there. Instead, your hydrogen ion secretion step is powered by ATPases, either a potassium proton counter exchanger, notice an ATP is used to do this transport, or just a plain old hydrogen ion transporter here, similar to what you might find in the stomach, okay? These are used to secrete your hydrogen ion. You now have your usual association of bicarb and hydrogen ions to form water and carbon dioxide, okay? In the tubular lumen, carbon dioxide and the water diffuse across the membrane into the cell where they reassociate and form a bicarb and this proton, and now our bicarb can be reabsorbed through this bicarb chloride countertransporter, and our proton is cranked through, again, through these two ATPases, similar to what happened in the proximal tubule with your proton or your sodium proton antiporter. These ATPases crank protons through, and you can, quote, recycle protons by just secreting and then reabsorb, all right? And your bicarb, net transport of bicarb from the lumen to the interstitium, okay? Let's talk a little bit about how you might secrete bicarb. So this might happen when you have an excess of bicarb in the body, what you might call a metabolic alkalosis. We'll get to that soon, okay? There are actually two ways that you can clear excess bicarb from the body. One is simply reabsorbing less bicarb, okay? So you're leaving more in the urine. The other one is to actually secrete bicarb so that you end up with more in the urine, and the secretion is done in the collecting duct by type B intercalated discs. Remember, the reabsorption was type A cells. This is type B cells, all right? And if you look at this thing, all it is a flipped around A cell, all right? So once again, our transport is powered by these two ATPases, but instead of being in the apical membrane and transporting protons this way into the tubular lumen, they're now transporting protons into the interstitium across the basolateral membrane. We have a reassociation of bicarb in the interstitium with protons and the formation of carbon dioxide and water. Once again, these are permeate to the membrane, so you get carbon dioxide and water going into the cell, associating into bicarb and protons, okay? But now your bicarb is transported across the apical membrane through this chloride bicarb antiport, instead of across the basolateral membrane, which it was for the type A cells, now we have transport through the same transporter, but now on the apical membrane, where bicarb is transported into the tubular lumen and excreted in the urine. And you will note that our proton, once again, can be cranked through. This time our hydrogen ion crank is in the basolateral membrane, okay? So this is basically a flipped around A cell, where now what you're doing is you are moving bicarb from the interstitium into the tubular lumen instead of the other way around, okay? And that's pretty much how bicarb secretion can take place. All right, so that's it for video 1 and video 2. I'm going to talk about how you secrete excess acid during acidosis. And then in the last video, we'll kind of put some things together and talk about the kidney's place in overall acid base. All right?